Hi. So I welcome you to this presentation where we basically predicted the solar panel energy. So my name is Taha Mahmood, and I have with me.
Sheikh Abdul Majid.
So I'm going to be presenting. I'm going to be starting off with the introduction. So in this, we basically covered the introduction, the methodology, the results, and the future prospects. Starting off with the introduction. So our main objectives of this presentation was basically two things. First main objective was to gauge the importance of each factor with respects to the energy that was outputted by the solar panel. And then based on that knowledge, we basically wanted to predict how exactly will the future energy will be generated based on our current knowledge. So the data sets that we were currently provided were two main data sets. The first data sets were the system parameters, where we were basically provided with the JSON file, which contained the output of the solar panel energy. And the frequency of that data set was basically after every 2 seconds, and the date range was starting from 18th of March all the way to 29th of August. On the other hand, we also had environmental parameters, which basically was an Excel file, and this was the file which basically contained the inputs, where we had a variety of different features such as temperature, humidity, wind speed, radius, etc. Over here, it was less frequent compared to the output file, where there was a reading that was taken after every 10 minutes, and the data itself was quite shorter compared to the system parameter, where we only had data from the 17th of July till the 17th of August. Moving over to the methodology. So starting off with the methodology, we basically started off by processing both the input file, which was the system parameters, and the output file, which were the environmental parameters. So what we did was we basically inputted. So we started off by using the pandas data frame, where we basically read the CSV file, which was the input parameters file, using the pandas function. After inputting the file, we basically um, did a series of data processing, such as removing the null values, making sure that this data itself is standardized, and also making sure that the data itself is consistent. And then after that, we also did the same pre-processing with the output file as well, in which we were basically provided with the JSON file. However, processing the JSON file was a bit trickier compared to processing the CSV file, where we basically had to utilize a library known as flattened JSON to make sure that the pandas is able to read that JSON file and segregate this into appropriate columns properly. So over here, we used a series of codes, and eventually we were able to process the JSON file. After that, we merged the both files, and the way we merge is that we basically so since the input file, since the output file had readings on multiple levels, then what we basically did was is that we basically took the sum of all the outputs that we had on 10 minutes basis. This is to ensure that the data frequency in both the input file and the output files were the same. After aggregating the data on the 10 minutes basis on the output file, then we basically did a one-on-one mapping between the inputs and outputs for accuracy. So over here, just like I mentioned, we had five inputs, which was the temperature, humidity, wind speed, the clearance index, monthly global, and the irradiance as well. On the other hand, we only had one output, which was the units that were generated by the solar panel. So this was the correlation that we created of each feature against the units that were generated. And as you can see, these three features, which was CMH, GHI, GHI2 correlation, and GHI final, which these were the three features which had the highest correlation against the units that were generated by the solar panel. And similarly, we also have a data visualization, which basically shows that there's almost a linear relationship of the GHI, which was the irradiance value, against the units that are generated. Now I'm handing over to Majid, who will be basically explaining both the linear regression model and the random forest model as well.
Hi, so I'm Sheikh Abdul Majid, and I'll be continuing this presentation from the model building part. So first of all, I would like to discuss the linear regression model. So in this model, as you all know, that it is the simplest model for machine learning, and it provides ease in terms of estimation. So first of all, we for like to make the foundation of our model, we started with the linear regression. So what this basically do is it maps the input against the outputs, and by it assumes that the data relationship is linear. So as you can see, the example has been provided for the conversion of degree Celsius into degree Fahrenheit, in which we have this equation: Fahrenheit is equal to 1.8 times degree Celsius plus 32. So it's a kind of linear equation model which we have learned, which is like y is equal to mx plus c, where m is the gradient and c is the intercept. And similarly here, instead of having one feature, we have multiple features based on the number of inputs which we take into account. So as you can see in the parameter coefficient chart, we have a number of features available. All of these were trained in the linear regression model, and for all of these features, we have this coefficient value which has been presented in this histogram. So the top four coefficients which were selected were GHI final, GHI correlation average, DHI final, and GHI correlation average, GHI1 correlation average. So here basically GHI stands for global horizontal irradiance, which is the property of the solar panel, and it shows that being the highest in terms of coefficient value, it plays a major role in determining the energy output. Moreover, if we talk about the score or the performance of this linear regression model, we can see that the mean squared error was found to be 53,201.2, while the tune R squared was found to be zero point 0.7, which was close to 1. So this model shows a decent amount of accuracy in terms of predicting the energy. Now we move to the random forest model, which is a more robust model in terms of accuracy as well as in terms of predicting the energy output. Moreover, one of the major advantages of this model is that it prevents overfitting. So it helps us in making accurate predictions regarding the test data as well. So regarding the methodology of this random forest model, it basically averages the predictions from multiple decision trees in order to achieve robustness. We have also mentioned the equation for this model, which is the average of the number of trees which are being used in the random forest model. Here trees represent here we have multiple trees, and for each tree we have a number of observations, and based on the majority voting, the observation is selected, and then overall the observations are averaged out to predict the output, which is in this case is energy input. Sorry, energy output. So as you can see, we have this here. We have also explained the equation, which is prediction is the final output, and is the number of trees in the forest tree, and tree represents the individual decision trees input. Now moving to the performance evaluation of this model, the tune mean squared error was found to be 21,917.9, while the tune R squared was found to be zero point 0.9. So if we compare it with the linear regression model, this model is comparatively very accurate in prediction of the energy output from the solar panel. So again, we have listed the top four coefficients, top four input features in terms of the importance of coefficients or the coefficient value for this model. And again, we can see that the global horizontal irradiance has scored the highest in terms of the importance for this model. Now moving to the time series plot, we conducted a time series analysis as well for the data which was provided. So first we resampled the data for every 6 hours interval, and then we aggregated the data to obtain the sum of the energy generation within each interval. So in this way, we were able to compare the day and night fluctuations for the energy output from the solar panel, and we were also able to determine the seasonality of the data. As you can see, a cyclic trend is generated. Cyclic trend can be observed from this plot, which shows that during the daytime the energy output from the solar panel is highest, and then it goes down. So there is a series of crests and troughs in this graph. Now moving to the autocorrelation, we have this autocorrelation plot as well, which basically helps us to determine the correlation between the energy output with time. So basically, this autocorrelation function was visually represented, and the lag value here was used to be 1, because the lag value 1 represent that for each for every 6 hours the data was compared with the last 6 hours. It shows that as you can see in the previous plot as well. So here we just determined the correlation between the first 6 hours and the last 6 hours. So the autocorrelation was found to be equal to 0.96, which means that the units generated were very strongly correlated with each other uh, with respect to time. So talking about the results, we have compared the linear regression and random forest here and we have compared the model accuracy. We can see that random forest has performed comparatively very well as compared to the linear regression model. So, and this brings us to the conclusion that this random forest model is quite accurate in terms of preventing overfitting and to accurately predict the energy output from the solar panel in the long term. For the time series analysis, as I mentioned, that we used the value of lag to be 1, and we found a strong correlation of 0.96 between the energy output for the current 6 hours and the last 6 hours. So it shows that the energy output is very strongly correlated with each. The values of energy output are very strongly correlated when it comes to analyzing them in terms of time series. Thank you so much for your time, and this was all about the energy prediction model for our project.